Okay, hello everyone. So this is a presentation on model estimation. I know you've been working on this already for the past week. So what I want to do in this presentation is truly to at least take a peek at the frontier, or at least at the general landscape of the research part of model estimation for agent-based models. And and hopefully get a good view of all the tools that are available, what's good about them, what's bad about them, how to pick, that sort of problem. So we're going to talk. The first thing, I always try to take a step back before we go into techniques. I always want to talk about identification. I want to talk about why estimation is so hard. And then we will go into the techniques themselves. And how to use them, and then practicalities, how to pick, is there something that's better than the others, that sort of problem. So estimation identification, by now you should be familiar. So you want to build a model, you want to build an empirical model, and that involves at some point fitting it to the data, right? If you think about linear regressions, right? Linear regression, the model itself is a linear model, which depends on certain parameters. And then the regression, the fitting, is the process of setting those parameters such that in that case, they minimize the mean square error, right? That's what fitting the model to data usually means, is that the model depends on some parameters and you want to use the data to inform them. Right, that's what fitting really means. And so the question is how to do it, especially with something as complex and generic as an agent-based model can be. One way, at least for certain parameters, because usually it's a mixture, certain parameters can be plugged in directly. So imagine let's imagine a model about epidemiology. The number of people in a city, for example, that's probably a number you don't need to estimate statistically. You can just plug in because it's fixed in a way. Some of them, particularly if you come from micro simulation backgrounds, there's some techniques to go from a sample of the population to the whole, or from the population to a sample. There's upscaling, downscaling problems. They're very specific to certain problems. They're quite controversial in some applications. And really, they're very dedicated to certain topics. Usually, if you cannot plug in directly, you're stuck with statistical estimation. That is, you're trying to find some technique for which you modify the parameters of the model, usually treating it as a black box, and trying your best to get a match of some kind that informs you about the quality of the parameters. It's a tweet by not so long ago by Edmund, was talking about this kind of problem. There's some parameters, right, that you feel right changing. For example, he's making the example about the chance of infection in an epidemiological model. Sounds quite normal to call it a parameter, but perhaps the age of distribution of the agent is not, because it's something you plug in directly. And the truth about it is that it really truly depends not so much on the nature of the problem or the nature of the data that you have, but really about the model itself. So let me give an example. This example I give often, but it's quite useful. So I build a lot of models of fishing and agent-based models of fishing. One key parameter of it is just how many boats are out there fishing. Now, you might have from data the right number of boats. So you know that in this lake, there's 72 boats that go out every year. So if one of the parameters of the model is the number of boats, you write down 72, right? That seems like a clear case of plug in the numbers, no need for statistical estimation. But now imagine that the boats are slightly heterogeneous, right? Maybe some are bigger, some are smaller, some are driven by better captains, some are kept better engine, and so on. Now, you can ignore heterogeneity. You can just do a model where there's 72 boats, in which case you sort of lose a bit of realism, which may be good or not. Or you accept heterogeneity. So you say, okay, no, there are 72 boats, and then I'm going to do as a parameter of these boats. I'm going to do their size, their captain skill, the quality of maintenance. And what you end up doing is that you are starting to get more complexity and more parameters. So even though you can plug in that there are 72 boats, now you're stuck with trying to estimate the captain's skill, which is very difficult to get unless you have very specific data. And the other way about would be I just abstract away. I don't even look at number of boats. I do a model that's simpler, with something like fishing power or some other abstract theoretical concept. And now I lose the data. I cannot use the fact that there are 72 boats, but maybe it's easier to estimate. So this is a simple problem that, depending on how you choose to model it and depending on the data available, can go from being a plug-in problem to being an estimation problem to being an estimation problem and throwing away data in order to make it simple. So it's actually quite, there's not a single, and this is true for all problems related to estimation, there is no real simple, hard and fast rules to set this up. And now this is something, so the important thing to understand is that estimation tends to be difficult because of what a model is and what the data is. So a model is, so of course, everybody come up with their own definition, but a model is eventually a collection of causal relationships, right? It's a collection of mechanisms by which variable A affects variable B through variable C and so on. And in agent-based models, these are embedded in algorithms. So it's when you code in NetLogo or whatever, that agent looks at X before doing Y, you're really embedding that causal relationship in the NetLogo code. And it depends on certain parameters, right? Otherwise, it wouldn't be a problem. But it is fundamentally, by its own nature, a counterfactual problem. That is, the model is supposed to tell you what is going to happen if something were to change. So if I go in NetLogo and I click on a turtle and change its energy, double it, right? What's going to happen to the whole system? That's what the model is supposed to answer. It's a purely counterfactual product. Instead, data by nature is factual. It's not about what things could have been, but how things are, right? And that's fundamentally the problem of estimation, is the problem of the historian, right? You see something that has happened, but you want to say what could have happened at something changed, right? You embed it in the model, but if the model depends on parameters and the parameters depend on looking at the data, you're sort of, it's not necessarily the case that you're able to inform entirely the counterfactual nature of the model just by looking at data. So, and this is, of course, the problem of induction, right? You want to set parameters which are counterfactual by nature, given that you only see observations. What could have happened given what had happened? And so before we jump into it and you go through all the techniques and you run them all, before asking yourself, let's do it, how to do it, you really have to ask yourself, can it be done? Because it's not always the case that a model can be estimated. And it really depends. It depends on the kind of model that you have. It depends on the kind of data that you have available. And sometimes, or this is less important, it depends on the technique that you're using. Sometimes it just cannot be done. And most of the time it will be done only in parts. We'll go through this. We'll try to understand how to diagnose these kind of problems. Oh, sorry.
Allora, questo è uno, vabbè, però tu R effettivamente non lo conosci.
Oh, sorry. Okay, so this is, in statistics, this is the problem of identification, right? Identification, a model can be estimated from data, is identified if there is a one-to-one mapping from the parameter to the data and back, right? So if I see the data, there's only one kind of parameter that could have generated it, and the other way around too, which is not always very common. The classic problem with is observational equivalence. We'll go through some examples in a sec. So one thing that could happen is that there is no way to tell, given the data you have observed, what could have caused it. There are many different parameters that generated the same thing. This is equifinality. This is sometimes due to the way the model works, or sometimes the way reality works. And sometimes it's just a problem. You just have data that is not very informative, right? Sometimes, and usually we call this a problem of under-identification. The data cannot inform all the parameters. Maybe it can only inform some, maybe it can inform them in a proportional to each other. I know that parameter A and parameter B have to together sum up to something, but I don't know exactly which is causing which. And sometimes you just don't have enough data, but if you don't need data of different nature, you just have to collect more of it. So this can happen for a variety of reasons, but it happens relatively frequently, and it's important to figure this out and to diagnose it. So let me just give an example of something you might be familiar with, which is technological adoption, right? So classic BAS curve model. There's a new technology coming around. People can choose to adopt it or not. And this could depend on a variety of reasons. Now, imagine that you have a model with complete perfect rationality. Everybody's very well informed about this new technology. They can decide whether to take it or not. Maybe the unknown parameters is how much they like this technology, their kind of utility they get, and maybe their budget constraint. If you have enough perfect rational people and you collect the technology adoption curve, it's actually very easy to go from the curve to what's the utility that they would have chosen. Why? Because the way they make choices is very direct, it's very informative. So in a model with perfect rationality tends to be a model where parameters match the data quite strongly. But if you start adding inertia, and in particular start adding multiple sources of inertia, for example, imagine that people can choose not to take not to uptake a certain technology either because they're lazy or because their friends are just more conservative, so they have to look around. Well, if the only data you have is whether or not you decided to switch to a new technology, it's impossible to tell whether it's because you're lazy or because other people around you convinced you otherwise, right? So classic problem is classic source of under-identification is the model itself. Is when you have multiple paths to explain the same thing, it then becomes impossible once you observe that thing to tell which was the path that generated it. And this, which is a problem that we can describe in words, comes up statistically, comes up in the way the mapping works and the way it fails you. And so sometimes it's the quality of the data that matters, sometimes it's the assumptions, and sometimes the connection itself. So another classic example of under-identification, two people sit on a scale. The only data you have is the total weight, the sum of the two, right? Because they're on top of the scale at the same time. You get a number, 200 kilograms, and then you're asked, how heavy is person number one? You can't tell. Why? Because the only data that you have is the sum of two parameters, and there's no way to split them apart. Another example more about weak identification is, okay, I want to know if somebody is throwing a coin and whether that coin is fair or is loaded. Maybe head comes up more often. If I only see two observations, it's impossible. It's impossible for me to really make a strong claim of whether or not the coin is loaded. What I care about at that point is the uncertainty, the confidence intervals around those parameters. And it's hard to tell with just two observations, a classic case of weak identification. And another thing that could happen is that the model, even though it starts from exactly the same parameters, due to some path dependency, can end up in one equilibrium or another. At which point, given that I know that it's been in one equilibrium at the end, it might be impossible for me to figure out what was the starting condition. So it's a classic example of under-identification. And although in agent-based models, it's not usually as clear-cut that I can immediately, just by listening to the description, tell whether under-identification can happen. In general, the complexity of it, the multiple pathway of the way things connect, make it so it tends to happen that under-identification is quite rife. So here's an example. This is an agent-based model example. This is an HIV model about HIV treatment. So the way it works, and this is a short paper, so it's worth a read. Just because it's an interesting topic. Fundamentally, the model is almost a microsimulation. So a patient will show up at a doctor office. The doctor will measure its white blood cell count, And then depending on a threshold, say if it's below, if I remember correctly, 300, they will give a treatment. Otherwise, they will not, and wait till the next time the patient shows up and do the same test. So this is a classic loop where the agent will go through to the doctor, then get treated or not, then go back to the doctor. And this is a classic loops like this tend to generate identification issues. The problem here is as follows. The question the authors are asking is, if I switch the threshold, so instead of 300, now I'm going to give the treatment as long as the white blood cell count goes below 350. So I make a treatment more common. Well, can I figure out from an experiment like that what is the actual direct effect of treatment to survival? And the answer is, once you go through this model, they clearly shows that it's impossible, because even if you start doing some localized experiments where you shift the threshold for some people, eventually, say for one round, because people keep showing up at the doctor over and over again, it becomes impossible to tease apart the direct effect, long-term effect of one treatment to the long-term survival probability. It's very well described. The model itself it comes up with a lot of these causal diagrams. It makes it easy to follow, but it's a good example of, it's not the under-identification simply occurs because when agents tend to adapt in particular way, or they tend to follow certain patterns, and those patterns tend to remove the effect of a shock, and so you cannot estimate the strength of that shock just by looking at what happens at the end. This is not a problem just of agent-based models. It's a problem in social science everywhere, right? This paper, it's now 10 years old. It's a paper about equation-based models of economics, DSGs, and what it was showing was that poor identification is pervasive in these models. Why? Because in macro models, so many things are happening, so many frictions, it's impossible to tell what's causing what. And in fact, the problem in that field is not so much one of calibration, it's one of validation, it's one of all the tests that were devised to check if the model was right, were actually showing that the models were very good at fitting stuff, but then testing it a little bit deeper showed that it was not the case. That the validation techniques were not helping. They were wrong with a very high degree of confidence. So these things are not necessarily just related to agent-based models, but with simulation, you just have to be more careful. And so now we're going to go through the techniques. I'll try to highlight which techniques tend to be more tend to make the testing of identification more salient. But in general, it can happen. You can have a model that you think is right. Theoretically, that's how you built it. You're quite confident that that's the way the world works, at least for what you care about. At which point, if you cannot identify it because you don't have enough data, because the model itself cannot be identified, you sort of have to accept that is a possibility, and then use methods that sort of are honest. You can immediately tell yourself, okay, so I have an identification issue, and then check if anything can be done with deep uncertainty methods or sensitivity analysis or validations. It's not so much, sometimes identification is lost, and that's the way the model works because that's how the reality works. And so you sort of have to deal with the fact that all your conclusions are a lot more uncertain. The other way is you change the model, right? You start adding assumptions, you start making, you start cutting off causal paths, or make the model simpler in certain respect, or make, there are many different ways to simplify the model so that you achieve identification, which is very classic in econometrics. It's something we do all the time. But you are subject to a law of decreasing credibility. That is, the stronger assumptions, the stronger your assumptions, the sharper your results, the more identified the model gets, the smaller the confidence intervals around the parameters you've discovered, but you'll be less credible, right? So you're sort of stuck in this, loop. Yeah, so that's a long introduction, but it's important because identification is a serious problem. And if you just ignore it, if you just go straight up immediately to look at how to fit models to data, you might not know you're stepping into that kind of problem because it by itself, you will not notice until you test for it very carefully. So let's just go through this. So one, estimate the model, right? Eventually, what we care about is finding the parameters. There's two ways to really look at how estimation works in a simulation model. You can do it sort of naively, right? You try to match a curve, right? I call this naive for a reason. I'll try to backtrack a little bit on this, but let's go through it. So you can just try to match a curve. That's the easiest. It's probably the most common way people do it. Has some advantages, some disadvantages. You can create a likelihood or something like a likelihood function. And if you're familiar with it, that's the classic way to do it with equation models, and then maximize that. Otherwise, you use summary statistics. You have maybe multiple curves, maybe multiple facets of reality that your model needs to hit all at once. Summary statistics is a way to go about it, and we'll go through it. And then, so that's one way to look at it. The other way is how you actually perform the estimation. And this can be done through fitting by minimization. So you just try to match something, try to minimize an error of some kind, minimize the distance, or straight up through a regression. Yeah, let's go through it. So what we want in a method, we want them to be efficient. That is, you've run now agent-based models for a while. A lot of agent-based models are slow, which means that you don't want to run it many times before finding the parameters. So any method that promises you to find the parameters given fewer runs, you would like to take it. So you'd like the model to be, you like the estimation procedure to be efficient. You would also like the estimation procedure to have some theoretical guarantee. That is, you'd like there to be some theorem out there that says that if you keep collecting data, you will at least be consistent. You will converge the real, true parameters of the world that generated the data that you observed. This is really important in economics, right? If you look at the economics, the way they insist on the difference between the word estimation and the word calibration, it tends to be about theoretical guarantees. In other fields, they don't care at all about this. Confidence intervals, you like models, estimation procedures that not only give you a parameter, but a confidence interval around it. This is very important in fields where the key question is where the parameters actually matter, where you find the parameter, say, of infectivity, and if you have a confidence interval around it, you can say, okay, so I'm really testing if this confidence, say, a p-value problem, is this infectivity rate higher or lower than a threshold for us to do some stuff. And that requires confidence intervals. So not just point estimates, but full plus or minuses. And the last thing is one of the most important is this method easy to use to test whether the parameters I have found are actually good, actually the ones that generate, or is there many other parameters that would have generated more or less, that would have been good enough, that would have generated the same curves or the same distance that I'm trying to match. So can I test its identification? Let's talk about naive methods. You should be quite familiar with it by now, right? There's a curve somewhere, right? House prices, for example, house prices in Italy in the past 10 years, you have a model real estate. You want the curve that comes out of your model to be exactly on top, or as close as possible to be on top of the one that's observed in reality, right? Problems of doing this, you can do this, but the problems is, first of all, you don't get confidence intervals, right? You get point estimates, you get, the closest curve that you can generate as parameter 1 equals 2 and parameters 2 equals to 10 or something, but you don't know how much you can vary them and still get the match. And there's no particular reason to think, even if you get some numbers out, that you actually achieved identification. There could be very many more parameters out there that could have generated the same curve, or generated curves that are almost on top of, almost as good, but you rejected them because the method usually involves minimizing. So try to find the minimum distance or the best possible match. And so you tend to risk losing observations that for just very small amounts are matched not as well. And that's usually a problem because those little differences could be due to simply data collection rather than the quality of the parameters. It's also very expensive to test, in that if you really want to know if the model is identified or not, you sort of have to redo this match multiple times to test how good it is. So it's difficult to diagnose how good of a match you're actually getting, how good it should be given the model. And so the problem with these naive methods is then you need to do a lot of sensitivity analysis. You really need to be careful. You don't know the confidence intervals, right? So you need to test very wide to be told, so if the parameter, once you set the parameters, you have to search in a large neighborhood around them to make sure that whatever the model is saying is not too sensitive or not too insensitive to the parameters you have found. And validations need to be thought, right? You have just matched a single feature of the world, but if you maybe check something else, it might be less realistic or more realistic. The consequences of doing simple estimations, in this case naive, I call it, geometric would be a better term, is that you really need to validate it. You really need to look at other features of the model and see if they are realistic, if there is any data to inform them, or if there is expert opinion of some kind. You really need to be careful. And so that's the problem with naive methods. However, and I'll try to explain why, but if you stay long enough in doing estimation of agent-based models, you sort of go through a 3-step phase where you go through initially, just because you start doing naive estimation, right? You try to match two curves, and then once you start learning more about the procedure, you start doing really deep. Oh no, I gotta use summary statistics with Bayesian priors. I gotta use metamodels. I gotta use theoretically guaranteed methods. But once you're really familiar with the methodologies, you tend to go back to naive estimation. I'll try to explain why. But let's go through all the other methods, explain what's good about them, and then try to backtrack why you're often left with doing naive estimation anyway. So one thing you can do, and one thing you do all the time with equation models, is likelihoods, right? So you take a function, you take a model, the model depends on some parameters theta, and there's a set of equations that generate some output. The way likelihood functions work is you build them by putting certain assumptions about noise and about how this function works. And then you sort of backtrack the other way around. You have a likelihood function. Likelihood function is not a probability. It's just a sort of score function that says, okay, given the data that I observe, how likely, but really, what's the score that you give to the parameter set I'm using? So for example, this is an example with one parameter, right? One model with a single parameter. If I do 0.5, right? I look at the data that is fixed. I check what's my score at if theta is 5, and they will tell you, it's something along the line of 3. Okay, what if my theta is 75? I check, the score now is 0.5. And so I can climb this function and get the best score. And so likelihood, so I look for the parameter set that maximizes the likelihood, that gives the highest score. And the good thing is that problems like these have a clear definition of optimum, right? There's a function somewhere, and you just have to climb it. So it's not that it follows straight from the assumptions you've made. It's quite clear, quite transparent what you're trying to do. However, one other good thing is that if it's an equation model and you look at these likelihood functions, you can immediately spot certain kinds of identification problems. Why? Because the theta which depends on, this is a vector, so it might depend on multiple parameters. Some in that equation could be multiplied away or subtracted away, and so they disappear from the likelihood function, in which case you immediately know that you are in an under-identified world. So there's three great things about likelihood functions. However, by themselves, with just the assumptions you get, they tend to produce point predictions, not confidence intervals. And that's a problem, because then you don't know how good or how far off you are from, or how acceptable small deviations from those parameters can be. And so you need to do, again, very large sensitivity analysis once you find them. And the maximization function could be hard. But the real problem is that agent-based models have a lot of great advantages, right? They're very they're very expressive. You can build theories very quickly, but the cost is, it's almost impossible to backtrack, what the likelihood function is. Here it's not so much they do not have a likelihood, this is quite wrong. It's they do not, that the likelihood itself is intractable. And it's often very unknown. So it's impossible. There is an equation like that, given the assumptions you made in the model, there's got to be an equation like this you could generate, but it's almost impossible to do so. And for all practical terms, there is not a way to get them. But if your model is very fast, you can use two substitutes, which is the Monte Carlo likelihood and the pseudo likelihood methods. These work, and these are quite, they have quite strong theoretical justification for existing, but they're extremely expensive. So let me just show an example how they work. This comes from this paper by Houghton. This is a very cool paper. It's a demographic paper, but the example they use about counting salmon, which to me is a big point. And so what they're doing is this. Fundamentally, the model works like this. There is every year, so you tagged 100 salmons. I don't know why, but they come up a river every year. And every year you have a chance of observing them. You pick them up, you check the tag, and then you let them go. But of course, a lot of them escape. So it's not like you can catch them all. You track a set of animals each year, because they come up with this river once a year. Each year they have a probability of survival, right? Which is what you care about. You're trying to figure out natural mortality of the fish. They have a certain probability of survival, and if alive, you have a certain probability of catching it, so tracking it or finding the tag in some form or another. So if I have, say, I'm tracking 100 of them, 150 of them, and I have for the past 5 years a time series of yes, no, have I spotted it this year or not? Can you find out this parameter, right? Can you find out theta? Can you find out also your efficiency? And this is, so here immediately, this is an empirical problem where you're trying to find this parameter. This parameter matters to you, matters to the biologist. This is a very important parameter to tell, how good the fishery is doing. Can you figure it out? This is a classic estimation problem. And so what you get in a model is something like this. This is the real data that is observed. So each light colored box, so this is what, over 10-year observations. Each light colored box is I have observed it that year, and each dark color means for this fish, so there's 200 of them, this fish was not spotted that year. And this is the observations simulated in an agent-based model. So the question becomes, how do I modify, or how do I find the theta and the p such that they maximize some form of likelihood? So the MC likelihood works like this. You start with random theta and p, so the two parameters that you got. You run the simulation with this fixed parameters many times, and then you check the score. The likelihood you give is how many individual time series match entirely what is happening in the world. So for example, this is a 10, this is a 10. So let's take fish number 200. And this was spotted on year 1, year 2, year 3, year 4, but that was not spotted anymore. The observation here for 200 simulated was spotted, not spotted, not. So this is wrong because it was not spotted in year 2 and year 3 while it was spotted here. So the score of this is 0. Then you try the next one. The next one is correct because It was only spotted in year one. It was only spotted in year one. So that's 1 point. And you go through all of them, and then you sum up how many points have you got. And that's all there is. You do it multiple times. So for the same parameters, you generate many of these samples, and then you have a score that you give to theta, to the pairing of theta and p, such that you just give them a score. And then what you do is that you keep changing these in order to find the pair that gives you the maximum score. So relatively straightforward, but extremely expensive, because you have to run many simulations for each pair. And so it becomes really important to get the right, to suggest the right pairs, and a maximization problem. Pseudo likelihood, slightly different. Fundamentally starts the same. Pick the parameters, run many simulations, but then you don't really want to do the full match. You just want to do individual match for each time point. So for example, here the score would be, if you look at fish 200 was a lot, tracked, and then not tracked. Here, the first one is a match, that's 1 point. The second one is wrong, so no point. Then it was not right, so again, no point. Then it was right, so 1 point, and then here was always right? So not tracked, so 1.1. So eventually, this means that this is 8 points for fish 200, and so on, and you start counting, and eventually it's the same. You just, there's the score numbers are going to be different, but you look for the ones that you look for the parameters that maximize these scores. The great thing about it is that as long as you are able to run models, you don't have to add any special additional assumption. This all comes out of the way you built the model, but the problem is, the problem is that it's going to take you a very long time, especially when this is a single kind of data observation, right? Have I spotted it or not? It becomes more difficult when there's like actual numbers, or there's multiple various kinds of observations to weigh. But that's fundamentally it. If you can run the model many times, run this. It's computationally expensive. It only creates point estimates. So you need to do validation, you need to do sensitivity analysis. And especially for MC, and especially for models that change a lot during the process, getting exact matches is very hard, right? So you will have a lot of likelihoods, a lot of simulation where likelihood is going to be zero, almost zero. And that's sort of a waste. And yeah, so this was an example where, again in demography, about, they could find some numbers with likelihood, but then when they did tests by doing validation, non-random holdout tests, it turned out that the results were quite garbage. So even though it's possible to do it, it's extremely computationally expensive. And he also has the fact that even though matches are very unlikely, sometimes you care about certain matches more than others. So like often, I don't care if 200 is actually the same, right? Most of the time I care on average, how many did I observe every year? How many did I observe every year? Is it about right? So this is really where you go with summary statistics. So summarize the real world data into a set of summary statistics, say average amount of salmon I've observed, or average amount of failures to observe, or variance or standard deviation, something like that. You come up with a few, not necessarily a few, but with a bunch of numbers that describe your data, a bunch of numbers that you can simulate from your agent-based models. And then you try to get them as close as possible. You sort of go back to naive curve matching, but more generic, more about any sort of number, any sort of vector of numbers you can try to get as close as possible. There are two different literatures that deal with it. One of them is called direct inference, more common in social systems, particularly in economics. And one is just approximation computation, which is it uses Bayesian stuff, so terrible, but it is more common in ecology, in particular, when it comes to agent-based models. It's very similar to, you might have read this paper, pattern-oriented modeling, where fundamentally the author there, Volker Grimm, went, at the end of the day, I have certain patterns that I want that describe reality, right? And then I want the model to generate the same patterns. And that's how I sort of judge whether or not the model works. Every other fancy stuff is not that useful. It really, the numerical version of it is using summary statistics. So let me just go through the way indirect inference works, which is as I described. You have a model. This model gets some parameters theta, generates simulated data, then there's real data, and instead of comparing it one against the other, like I was doing through in the likelihood or even just in the naive catch curve, I use an auxiliary model. I use something to summarize it into a set of into a vector of numbers beta, and then I try to change the theta here in order to get the two betas to be as close as possible. So an example of this, let me go to this. An example of this is Zhao. This is dissertations from a few years ago now, but dissertations are long, but this is a good reading. It's a financial model, and what she had was, a financial simulation generates enormous amount of stuff, like who's owning what, and a lot of this we don't have data, so it was impossible to do a pure likelihood method. So what she did was, at the end of the day, what they cared about was, are the prices that are generated by the simulation similar and react similar to stuff as the ones in the real world? And instead of trying to match the price curves itself, they matched a regression that they run on the price curve. So the price curve will go on for years. There'll be many stocks being traded. So what they did is that they took all the real data, threw it into an AR-15, which is a time series model, and the AR-15 gives you 15 parameters. You do exactly the same in the simulation model. You run the simulations. You don't take the curves, the price curves directly. You put them into this AR-15 sausage making machine, comes out with other 15 parameters. Do they match? And that's fundamentally how it goes. And so it is, indirect inference is sort of magical because it's theoretically consistent. That is, as long as any model you're generating generates a single separate set of numbers. So there's a unique set of numbers, unique set of summary statistics that your model spits out. So as long as that is the case, then it will be the case that once you estimate a model, that model will be consistent. That is, if you can collect large amounts of data, it will emerge a single set of valid parameters will be generated. And if the model is real, that is, if the model is actually what generated the data, then you will have to converge in probability almost surely to the true parameters. So if you assume that your model is right and the model is generated, so the real data is actually coming out from some unknown parameters, then this method will eventually find them. And so these are weak assumptions in terms of proving it. There is no assumption about the distributional effects or what kind of noise it has to be subject to. And it does not depend on the kind of summary statistics you choose. It just has to be unique. But so behind this mathematical mumbo jumbo, what it's really coming about is, so if you assume that the model is identified, it is possible to generate a one-to-one mapping between theta and now not real data, but these summary statistics, then it must be the case that once I see summary statistics, I can go back to the theta that generated them. That's all that this is saying. But it's impossible to prove whether a simulation model is actually identifiable before running any analysis. And so these are very weak assumptions. And so this is theoretically consistent, but it's impossible to prove. And it's probably not true in the sense that in many agent-based models, you do an identification problem. You do not have summary statistics that are completely unique. And so it's sort of a bummer. But the indirect inference and summary statistics are at the basics of sort of all modern estimation techniques. And in fact, the good thing about it is if you're willing, you can create confidence intervals around the points that you've estimated. Unlike the naive estimator, there is formulas to guess the confidence interval, the Gaussian, so normal confidence intervals around the point that you've estimated. And that's fundamentally the magic of it. It gives you, it's theoretically consistent. It has confidence intervals, but unfortunately, it's only the case when you are studying something it's easy to identify, which is not usually the case. So the other technique that uses summary statistics is approximate Bayesian computation, which is exactly the same as indirect inference, but you add priors, right? Prejudice. You sort of have to, before you start the simulation of all the parameters that you have, you say, okay, they have to be within a certain bounds. I think this is uniform. I think this is normal. If you're familiar with Bayesian processes, that's how it works. In exchange, you get confidence intervals that are very responsive. You actually get posteriors, and you do get non-normal. So there's some cases where data sort of suggests that stuff is maybe power law. Some parameters could be that they're probably very small, but there's a chance they could be very large. Approximate Bayesian computation produces that sort of stuff quite nicely. It's much less efficient than indirect inference. It's much less efficient than running minimizations, but it's much easier to do identification problems, to check if the identification works correctly. The simplest approximate Bayesian computation is very easy to describe because it's just a rejection method. You start with some summary statistics of the real world, right? So familiar with this. You run the model many times, drawing the parameters completely at random every time. And then if the model spits out summary statistics that are close enough to the real world, then you accept that run. And then you run, you just do a posterior, you just produce a posterior given all the parameters that were accepted. So all the runs that were accepted. So this is a very good paper about this calibration, evaluation, and individual-based models using approximate Bayesian computation. This is a cool paper in ecological modeling. It goes all through the rejection phase and then the testing phase, because the good thing about this is that you can try, because you run the model many times completely at random, you can then sort of pretend that some of the runs are not from the model, but they're real, and you can test very quickly whether the other runs that you have generated can inform you about what the parameters are. So that gives you a very quick, very easy way to get identification issues, to see which parameters are identified, which are not. And this paper does a great job at explaining how to do it. It's ecological, it's about, if I remember correctly, mold, but it is extremely informative. So if you have to read a paper alone from this presentation, this is great for it, because it opens up the world to approximate Bayesian computation, and there's many different variants. Reference table, which are regression based, adjustments, MCMC, which is Markov chain Monte Carlo, sequential Monte Carlo. ABC is his own field, and it's now it was created for simulations, very genetics, but it's slowly getting integrated into agent-based models. You see them a lot more often now because it's extremely powerful. In exchange, of course, I mean, you sort of have to suffer the great sin of doing Bayesian stuff, but there's an extremely powerful set of techniques, and it's a whole literature, and that's a great place to start. And so now we're getting to the end. What I want to talk about is very barely. Okay, so we talked about sort of the ways to go about it, the targets, right? You can match a curve, you can match a likelihood, you can match summary statistics, and you can do this in a Bayesian way. You can do them, it's a simple maximization with indirect inference. But in practice, there's still certain details to keep track of. First of all these methods require you to run the model, right? You're familiar now with running the model. You're familiar how to build it. You're familiar how much time it takes. There's always a tendency to create very descriptive models because fundamentally you guys are scientists and you want to have a model that's at least verisimilitude. But it's not the case But the cost of it is that if the model is very slow, so will be the estimation, right? Because you just have to run the model many times. Estimation requires running the model a lot, so you get a premium on speed. You prefer models that are easier to run. So for empirical work, try to keep it as simple as you're allowed to. Keep it simple, right? Now, we talked about summary statistics very, very briefly because it's his own field. Fundamentally, you have to choose two things. Once you boil down, once you summarize indirect inference into a set of summary statistics and you're comparing the real one and the ones that come out of the model, you usually tend to write in a system like this. Is actually the square distance, that is the square differences between real parameters and simulated ones, right? And you want to change this, minimize this distance by changing this. This is the indirect inference classic approach. Really, it's the problem with this kind of field is that there's many different ways you can summarize reality, and then which you're then trying to match, right? And it's also difficult sometimes to weigh them. That is, summary statistics, you can generate a lot, but some of them are more interesting than others. If you're doing an adoption curve, maybe you have data on happiness of people who adopted, happiness of people who didn't adopt. Maybe you have some data you don't really care very much about, like I don't know, the kind of models that they're adopting or they adopted first. Then you might weigh the second kind of data less. And this is usually tends to be quite important, but it's difficult to figure out how to do it. So when it comes to summary statistics, which again is at the basis of all the estimation techniques that are now being really published, choosing these betas is very difficult. Choosing how to summarize the world is very difficult. And of course it is, because summarizing the world is a modeling question in and of itself. So the three questions: how do we choose them, right? How do we weigh them, which is this little formula, and how do we do the minimization? Minimization can be done, you can use genetic algorithms, you can use Metamodels, which are very popular. You can another meat, you can use whatever you want. But, and this is the problem, they tend to give slightly different answers. That is, this is not an easy choice, and it matters a lot, and it's quite expensive. So one thing that I propose, but not just me, is to sometimes, if you can get away with it, switch the minimization with a regression problem. So instead of trying to minimize or weigh the summary statistics, run the model many times at random, like you do the rejection, ABC, then create a table of parameters. And for each parameters, check the kind of summary statistics that they generated, and then do the problem in reverse. You have this table, flip it, and now run a regression where you're trying to predict what the parameter is given the summary statistics that you observed. And it's regression. This is a classic regression method. It's still based on summary statistics. You could do it on a curve matching. You could do it even on likelihood if you wanted, but you get a confidence intervals because your regressions give you that. They're easy to test for identification. You get all the benefits of rejection ABC. You also get the cost of the fact that you're sort of running it at random. So it's not very efficient. You have to run the model more. And there's a paper here where I do linear regressions, and more than the paper itself, you probably want to look at the literature review there. There's quite a lot of other techniques, especially random forests and neural network. This is a relatively open field of research, and it's particularly useful when you're really worried about identification, because that's really something that very quickly is apparent and can be tested. But the real problem at the end is that you have a lot of methods, you have a lot of way to set up the targets, you have different ways of weighing the summary statistics, you have many different ways of minimizing it or skipping it through a regression. Is there a way to tell which method would be better, right? Because that's something I really wanted to sort of, well, let's just all use genetic algorithms and summary statistics. And it turns out that, as far as I could tell, there's no real easy method that beats all the others. Fundamentally, there's no free lunch. This is a paper I ran on, I think 40 models overall with 20 agent-based models, and half of them were only partially identified. So this is published papers. These are not relatively difficult. They're all good, good models, but half of them, given the data at hand, could not be identified, or some parameters of them cannot be identified. So again, just to go back to the beginning, identification is a big deal. It's a big problem. You want to test it in your model because it will matter. And so half of those models were not tested, but the methods themselves, I could test which one got the parameter right, which one, which method which estimation procedure discovered the right parameters, and it turns out that it was a complete crapshoot. It was there was at least, so any estimation method was the best at something. At least once there was at least one parameter in one model where even the dumbest rejection ABC would do better than very fancy other stuff. So the key here is that you don't want to waste too much time hunting down for the best, the most optimal estimation method, because it probably doesn't exist. It is a difficult issue. Estimating parameter is difficult. You're better off, instead of trying to squeeze as much efficiency, as much precision out of stuff, figure out what you know. So figure out what can be identified and figure out to build confidence intervals. To me, my experience is always that that's the real important part. And that sets you up for cross-validation, sets you up for all sorts of validation techniques that you want to do. And carry over that uncertainty. It will happen. You will have models that the scientist in you knows are the better description of the causal mechanisms, but that the estimation can simply not identify, or not very well, maybe great confidence, large confidence intervals. That's something that you must be willing to accept. Sometimes you have models that are difficult to identify, but that's why because you think reality is complicated that way, and then you have to sort of be honest about the uncertainty. And so I close with this, so I have to backtrack that thing I was saying about naive models. So naive estimation techniques and theoretical guarantees. So there's a famous statement there by Box, all models are wrong, but some are useful, right? Although actually, but the more pragmatic way is all models are wrong, but some of them have 300,000 citations. The key there is about all models are wrong, right? So if you look at theoretically consistent models, which is ABC tend to be like that, and indirect inference, so but also likelihood functions, there is a tendency to rely more on them, because you can prove, somebody else has proved, some form of strong consistency, which tend to imply that given infinite data, we will be able to discover the true parameters, that the parameters that we're estimating will converge almost surely to the true values of the world that generated the data we observe. And the problem is, once the models are wrong, that's not the case anymore. There is all those proofs sort of stipulate that there exists something like the true value that you are converging to. And that's not truly the case once you start accepting the models are in some way flawed. And you know they're flawed because you built the model, you know all the shortcuts that are in there. You know that the model is not supposed to be completely isomorphic to the world. It's supposed to be a simplification. And so even though you can generate theoretically consistent theorems, that does not mean that they apply necessarily to the estimation at end, right? Which this carries on in validation itself. Sometimes we check validation is the model right? Is the model producing exactly what the data suggests? And you know full well that if you have enormous amount of data, you will have to find some problems with the model because the model is not the real data. It's just common even for just very simple normality tests. The model is not the world, that the model is not isomorphic to it. And you do expect it to have some validation problems. And so really at some point you have to, at some point you just start considering estimation itself as a technique to get parameters that get you close to the data in a geometric sense. They just, they sort of match what you observe. But then the real lift does not come from using a good estimation technique that, has theoretical guarantees, but by doing validation, right? By doing sensitivity analysis. So perhaps in the long run, the literature will focus a lot less on cool estimation techniques that are theoretically sound and more on just let's get quickly some form of parameters that are close to the data. Let's get quickly some confidence intervals around it, and then let's just focus on validation. If the model is there to predict, does it predict okay? Does it help weigh the evidence correctly? Does it simulate secondary effects as well as the first? So there's a tendency in the estimation literature, and you will see it once you start reading it, of conflating the properties and the problems of validation with the one of estimation. And that's something that I think we're sort of moving away from, but it's still there, it's still happening. And there's a nice paper here. This is again Bayesian, so forgive me for the sin, but this is a nice journal article, sort of trying to get across from simulation, from statistics, but getting to the same point, right? So, can we really focus more on the estimation, what they call inductive elimination, rather than just pretend that we can solve all these problems in an estimation format? And that the very last thing is much more practical. Is like there is a lot of workflows where you build a model and then you calibrate the estimate at the very end. And that's a very bad workflow in the sense that pride goes before the fall. You're sort of telling yourself your model, your theoretical ideas and insights are so good that you only need to check the data at the very end. And that's not a great way to either do science or to do estimation. You're better off doing estimation progressively. You start with a simple model, you estimate it, you check what's right and what's wrong, and then you see what the errors are. What's the problem? Even though I estimated, even though I try my best to set the parameters to get somewhere, they're wrong in this direction, they're wrong in that direction. Let's change the model, let's improve it a little bit. It's a process of overfitting. It's a process of calibrating, is sort of building the model, trying to fill in the gaps, which tend to generate sort of a hodgepodge overfitting models, but it's probably the best way to deploy estimation rather than waiting at the end, because of course you're going to be probably wrong if you just wait till the end. And so it becomes quite embarrassing. But yeah, so this was a long presentation. I'm sorry, because I talked the whole way through, but I hoped I managed to, first of all, scare you into thinking about identification more. Second, I hope you have at least a good grasp of where to look at for all these new estimation techniques that are coming out, but also, most importantly, a sort of cynical eye to just looking and taking estimation claims too seriously without remembering that at the end of the day, you're building a model that's necessarily wrong, and you're better off focusing effort on trying to understand how wrong is it more than hoping that estimation magic will come out. Thank you very much.
Yeah, thank you, Ernesto. Really, I appreciate also the recommendations, which you, very much in line with what we are trying to do here. So thank you very much, and we have some time for questions and comments and to Ernesto.
you want to say a few words about your free lunch package? I just posted the link in the chat.
So if you are, I guess you guys are playing with R a bit. So there's a package there which collects a bunch of ABC methods and regression methods for estimation. Mostly it tries to make it easy to do identification testing. And so there's an example there with shelling, which is misspelled. So that's great, a great calling card. But it's so if you're interested in regression-based methods, so try to stay away from maximization a bit. That's a good way to go about it. This package sort of it's really just an interface for better models and better packages. But that's sort of what I think was needed. So take a look. There's a couple of tutorials about it. But again, it's mostly a Bayesian approach with all its benefits and costs. So, you know, caveat emptor. There you go.
Yeah, thank you. So any question?
I have one.
Please, Francesca. Yeah.
Thank you, Ernesto, for your presentation. I would like to ask you a question about your last point. So, which I agree with, that models should be more assessed by when they fail. So, to try to find out when they fail. But why isn't there an emphasis to try to systematically find when they fail instead of when they do? So, I mean, this estimation, I think, that allow us to systematically search under a given method for the best parameters, but is there an emphasis to search for the worst parameters systematically, to say maximize the distance and then elaborate on this?
Yeah, so there's a paper, this is on sensitivity analysis. This was called Active Nonlinear Test by John Miller. This is in the 90s, okay? And what he was arguing was this. Okay, you estimate the model. This was, okay, so you estimate the model whatever way, right? This was in the 90s, so probably just, I don't know, throw darts and stuff. But anyway, they would get some parameters, they would get some output, some curve match. And then his argument was, and this is again, sensitivity analysis literature, why don't we just try to change all the parameters by at most 10%, and turn into a maximization problem where I try to do, if I can only change 10% or more, 10% or less each parameter, how far off from the curve can I get, right? So that kind of technique exists. It's also part of the QBEM literature, or at least papers. And so that kind of intuition is there, but it is a sensitivity analysis rather than validation point. Although, to be fair, you can use it for both. I guess the systematic validation just doesn't exist, even in that paper, which is statistics, so it's about regressions, because there's so many ways in which you can sort of invalidate a model. You can say, oh, what about the kurtosis, real life kurtosis versus kurtosis in your model? They don't match. So go read that paper by Shalizi. It really mentions that it really is about what you're using the model for, right? Validation is about usefulness, is about what the model is being used for. And so if you get some stuff wrong, it's okay if what you're trying to use it for still works in that process, right? So that's why there's no systematic validation technique, because it really is it's not even about the model, about the literature, it's about the use you're making of it. Right, and that's it. But that intuition there of maximizing, do check that active nonlinear test. I think it's the same author as the CAS book with Scott Page. So yeah, it only had 200 citations, but it's a really good technique, and it's quite fun. It's quite funny to just, you know, how bad can I get? Because his argument was, this is a world 2, right? So they were predicting sort of destruction of the world. And you can say, oh, if I change this by a few percent, suddenly there's like 20 billion people. So it's quite fun kind of sensitivity analysis, but that's where it is. That's as far as you can go mechanically.
Yes, thank you. Yeah, this kind of things about learning from failures. It's or low incentives for finding where you're wrong, and the great incentive for finding when you're right. It's a very big kind of issue in science at different kind of levels, not only this kind of things. Anyway, good point, Francesco. And any other question?
I have another one if no one else does. When you apply the regression technique, just like building a regression from your model inputs to your estimated parameters and then running it backward to get your inputs, how do you handle interactions between parameters?
Yeah, so seriously speaking, you don't, right? So the interactions, if the interactions are there, they should be somehow reflected into the summary statistics, right? This is a classic. So the first regression technique were in the ABC literature, and they mentioned this fear. It was like, it should, but somehow it just never comes up to be. But the neural network literature, especially Radvev there, which is in psychology. So I'll try to add that to the Dropbox folders for the students too. They claim to be a little bit better because they estimate all the parameters all at once, right? So in that case, you do get some form of interactions, because you're not estimating one parameter given all the summary statistics individually, but you're doing them all at once, right? But you can do that with linear methods, right? There is forgot what the proper term for those kind of regressions are, but like many-to-many, but it doesn't seem to have a lot of advantage. So you're right, that's a theoretical risk. Is something that's been acknowledged right from the start, but it just never seemed to sort of prop up. There's never a case where they could say, oh, that's the interaction that was missing in the regression. So it is a fear. It's definitely a weakness that it's identified, but it's how often it comes up. I don't know. We couldn't find a single example where it does.
So the question related to this is, given that we use ABM to explore, very complex nonlinear type of microcausal generative mechanisms, what are you going to miss of this kind of explorations, or the richness of this specific type of modeling framework, or when we try to apply to this conventional type or even advanced type of statistical kind of estimates about parameters?
Yeah, so this is a problem that comes up a lot in metamodeling, right? So now forget for a second estimation. There's a lot of work on metamodels, particularly Gaussian processes, which is summarize a difficult model. It doesn't have to be an agent-based model, but a difficult model with some statistical model. So a model does what? Takes the parameter, crunch them, creates some output. And maybe the model is too slow. And so what you do is that you run this slow model enough, and then you use this matching between parameters and summary statistics to train some meta model, and then use the meta model for it. And this is an old idea. It's very popular in ecology. You see a lot of papers with BACCO, B-A-C-C-O, Bayesian analysis of computer code output, and yeah, it's used, but it's not necessarily. Yeah, I share your same feeling. It's like, to a certain extent, you're gonna lose out a lot of what the modeling does. In particular, sort of you can trace what's going on in the model, right? You can see, oh, this happened because this agent did that, and it's lost with a meta model. But in estimation, we do the opposite, right? So we just try to go back from the summary statistics. So once you have the data, you want to go back to the parameters. So there's no dynamics that you're trying to catch. You're just simply saying, okay, given the observations, what could have generated it from scratch? And I trained it by looking at the model output. And so it's a slightly less difficult problem, and it's actually, this is important. So you'll see a lot in the literature, you see a lot of meta models applied in estimation, but it's almost always as a trick to get faster maximization. They're not regression methods. They're really there to the indirect inference, right? You want to, or likely you want to climb it, but climbing is too complicated. So I'm going to climb this meta model instead. And that's very different from regression methods, which is, I don't know, I just have the data. I'm not looking at the dynamics. I just want to move it back, map it back to the parameters. And sometimes they work, sometimes they don't. But the good thing about regression methods is that you can tell immediately. That's the thing. So it's not so much they're particularly efficient, they're not, but they are there. You can immediately tell if at least you can get back the parameters of the models they used to train it with, which is actually much more difficult than you think. So yeah, so the regression, if you're really caring about super precision or super efficiency, the regression method is not necessarily the best, but you can tell how good they are, which is very difficult to do in maximization methods. That's what really tells them apart. There's a diagnostics is what they're good at.
Yeah, good point. And if I like other things, if you project, I mean, the situation about, there's a lot of increasing interest about increasing publication, and you are involved in this about how to improve this kind of the methodology behind the assessment and evaluation of simulation output, especially in ABM. So if you think about, you close your eyes, you think about 10 years. What do you bet in 10 years? Where are you going? So what do you dream we all as a community going in given years about that kind of problem?
Oh man, the cynic in me says we'll go in cycles, right? The way I see it, a lot of frontier stuff is really about cool maximization, cool minimization. So right now you can use genetic algorithms or whatever. Now they're 10 years, they'll use some, neural network inspired minimization technique. I don't know if it's going to make them. So I think if nothing changes, they're just going to become a little bit more efficient, not a lot more efficient. We're just gonna do the same stuff with fewer simulations, which will, in my opinion, just make simulations way more complex, more descriptive. So I think that's where it's going. A little bit of computational advantages, right? Maybe we'll be able to deploy clouds better, right? There's already a lot of there's already stuff published on using clouds to sort of spread out, parallelize estimation. I think it's just going to be a little bit more of that. And we will match it by making the models a little bit more complicated. So we're back at square one. That's the way I really see it, which is not necessarily bad. It's just that, because again, my feelings is it will end up that estimation will be less important than we think. That it's really about the validation part. It's really about the sensitivity analysis. And so I think we're not going to do a lot of progress in the next 10 years. I hope I'm wrong, but we're not going to do a lot of progress, but it will not matter very much. I think it's going to be more, okay, let's do more sensitivity. Let's do more validation. Let's do this. I think that's where it's going to go. Where I hope it's going to go.
Yeah, good point. So any other comment, question? We still have some minutes left. Unless you want me to go on in, posing visionary challenging question to Ernesto. So, for instance, one of the questions about, especially for young beginners or young scholars in the field, one of the questions is about the availability of data. So, I mean, in my understanding, there are fields in which there's a more standardized way of getting data or transforming parameters in. So in economics, for instance, this is something very good. So we or in econometrics, we have this kind of conventional way of measuring something, cumulative ways of measuring something, and so in other field it's a little bit more fragmented, and so how can we do? I mean, how can we progress in a way of minimizing the possibility that the young scholar is getting mad in spending years in trying to get data, whereas maybe probably to estimate certain parameters where maybe probably, I mean, there's a lot of similar data on similar population that it's just a matter of bridging or connecting this kind of thing. So this is something is really, especially for certain type of communities, is really something that I see a great obstacle to the progress of our ABM community.
Yeah, I think it's because the ABM community is not organized around the question, right? Like, so I work a lot with fisheries, right? And fisheries, it's simulation models, not really agent based. And they tend to, because of course it's about, eventually at the end of the day, they want to know how much fish is there in the sea, right? A stock assessment problem. And so eventually they collect enough data sets about, you know, stock assessment around the world, or the kind of data they have to that they face tend to be sort of similar. Oh, they checked how many catches were there, or they checked the size of the fish. And so because of that, it tends to eventually push the field to deal with the data that other people have dealt with, you know, with the data format that other people have dealt with. And then they show up with eventually you get the same methods too, because they have a couple of R packages that everybody uses. So that's the way it's sort of, I don't want to say professionalized, but it's the way it sort of structured itself. For agent-based models, it's difficult because I could do that for fisheries, but like only 10 other people in agent-based model community would care, right? So yeah, so it's difficult that way. So, or at least the way I've seen it work in fisheries, and it does work there, is by having a common problem. And so I don't know, maybe it's really about, you know, setting some challenges in the agent-based model communities we should coordinate against or around, try to find out, you know, a priori what would be a good way to deal with them, and then see where that lands. I honestly don't know. It's tricky that way, because again, it's the good thing about this community is that, you know, you get to hear a presentation about urban dynamics, and then the one after is about fisheries. But on the other hand, you know, the technique themselves about building the agent-based models are there and can be shared, and we learn a lot from each other. But then the validation and the estimation problem, well, the estimation techniques might be the same, but the estimation problem, data problem, is completely different, right? Yeah.
Yeah. This reflects more, I mean, obviously the quality of the world community progress in specific fields, which is obviously diverse in each field. Yeah. Okay. Yeah. Any other questions? So we still have some minutes and try to explain Ernesto's time.
So if no one else has questions, I still have one. So depending on the estimation technique you use, you'll have uncertainty around your parameter values. How does that uncertainty translate into the uncertainty of evaluation of potential policies?
Yeah. So
basically, what does it buy you to know that?
Okay, so again, in some fields, like, you care about it just because you care about it, right? You want to do a p-test, you want to do, you know, here's a classic economics problem. You estimate, I don't know, the marginal propensity of consume. Is the marginal propensity of consume higher or lower than 20 or something like that, right? So sometimes you care about confidence intervals because you care about confidence intervals. When you don't, you're right. Then it becomes a question of, okay, so let's imagine that a parameter is between 0.1 and 0.3. Then you want to use that for sensitivity analysis, not so much of the model, but of the policy suggested, right? And so the thing that you really want to be worried about, and this is something that bothers me about sensitivity analysis, sorry. So sensitivity analysis often gets used to say, okay, if I change this parameter even a little bit, the model changes a lot. That's bad. And so we shouldn't do that. Although, of course, the model has to be sensitive to some parameter, otherwise, what's the point? What you're really worried about instead, what you should be really scared about, is the situations where the parameter is the model is very insensitive to that parameter when it comes to sensitivity. So the parameter could be anywhere because it doesn't really affect the way the data is generated, but then that same parameter matters a lot when you get into policy, right? That's the scariest thing, because now you have a parameter for which, if your method is good, the confidence interval will be huge, right? The estimation parameter, the estimation procedure doesn't know how to set it, so it just gives you a giant number. And then that giant number, when you actually test it, when you run the policies, you know, randomizing a little bit within their confidence intervals, you get huge explosions in policies, right? So to me, the confidence intervals immediately tells you quite quickly what's been identified and what's not. There's some risk to that, but it's useful. But then you can use it to say, okay, when I do policies, this one is small confidence intervals, I vary it only a little bit, and this one, giant confidence interval, I vary it a lot, right? And then you can really say, given the data, because that's what you care about, right? My policy suggestions, how varied they are once I start moving parameters, rather than the estimation itself, which is all likely, which is just a number, you don't care. And so, yeah, so you want to eventually use them. So the way we run it sometimes is, you know, if I randomize the parameters in their 95% confidence interval, what happens? What about the 99% confidence interval to the policy itself? So that's the way you use it. If you don't care about confidence interval for their sake, you usually care about it for policy simulations later on.
Okay, so there's 2 minutes left, but feel free to ask a short question, or coffee is out there. Well, not out there, but anyway, around us probably. Okay, so if there's no any common question to Ernesto, I would like, to thank Ernesto for this brilliant lecture, and hope that you liked it. And I remind you, for those of you who are probably would like to go back and see, slides or concept that Ernesto has shared, that, you know, at the end of this day, you will have the link to the Ernesto's video lecture, so that you can go back and also later and check and go back to concepts and learning more. So thank you again, Ernesto, and hope that we cross our way sooner or later, directly for a beer. And have a good day, remaining day. And guys, we will see each other at 3:45, so 15 minutes. 3:45, we'll be back. Thank you again, Ernesto. Well done.
Thank you all.
Well done. Ciao.